Hello, my friend, and welcome to the Quantum Slumber. I'm really glad you found your way here tonight. This is our quiet little corner of the universe, where we let big ideas move slowly enough for you to relax, unwind, and, if you'd like, drift off to sleep. Tonight, we're heading somewhere very small and very strange. We're going to sink down beneath everything you can see and touch, into a hidden layer of reality that's humming under your everyday life. Physicists call it the quantum realm, a place where particles can be in two places at once, where the simple act of looking at something can change what it is, and where the rules of our ordinary world quietly fall apart. This realm isn't a fantasy landscape from a movie. It isn't off in some distant galaxy. It's here, right now, woven into your body, your thoughts, and the space around you. As you're listening to my voice, quantum processes are shaping the light from your screen, the atoms in your pillow, and the tiny electrical signals flickering through your brain. For most of the day, you don't have to think about any of that. You just live your life on the surface in the familiar world of clocks and coffee cups and traffic lights. But tonight, you get to do something different. You get to gently peel that surface back and ask, what's actually underneath all of this? What is reality made of when we go as deep as we possibly can? As we explore this tiny, shimmering realm, there's nothing you need to figure out or remember. You don't have to understand quantum mechanics in any textbook sense. You can just let the images and ideas wash over you, like watching ripples move across a still pond. While your body grows heavier, your breathing slows, and your mind loosens its grip on the day. Before we step through that invisible doorway, I'd love to know where you're listening from tonight, and what time it is in your little corner of existence. If these quiet journeys into deep reality help you relax, you're always welcome to tap, like, and subscribe, so more sleepy minds can find this gentle space too. For now, just take a slow, easy breath. Let your shoulders soften, unclench your jaw, and feel the bed or chair supporting your weight. We're about to slip beneath the ordinary world and visit the quantum realm, the hidden foundation of reality itself. So, to begin, let's bring this strange idea down to something you can almost feel in your hand. Imagine you're holding a coin between your fingers. In the ordinary world, that coin is simple enough. You flip it. It spins through the air, and when it lands, it's either heads or tails, one or the other. Even if you don't see it yet, you know it has already decided. But now, picture a deeper layer of reality where that same coin doesn't have to choose right away. In this hidden layer, it can sit in a kind of soft in-between, not just heads or tails, but poised in a state that contains both possibilities at once. Only when you finally look at it, only when your attention lands on it, does the coin settle into a single outcome. That in-between, that shimmering space of possibility, is a tiny taste of what physicists mean when they talk about the quantum realm. Of course, in the real world, we're not tossing coins in quantum limbo. We're dealing with particles so small that they're far beyond the reach of our eyes. Electrons, photons, and other building blocks of matter and light. In this world of the incredibly small, the rules you're used to simply don't apply. Objects behave less like little marbles and more like soft, spreading ripples. Certainty gives way to probabilities. And the simple act of observing isn't just a passive act. It helps decide which of many possible futures becomes the one you actually experience. You might be tempted to think of this as a distant laboratory curiosity, the kind of thing that lives only on chalkboards and in research papers. But the truth is much more intimate. The quantum realm is not somewhere else. It's here, woven through everything around you. It's in the atoms that make up the mattress beneath your body, quietly holding its structure together. It's in the light streaming from your screen, packets of energy arriving in tiny bursts your eyes can never individually see. It's in the delicate electrical pulses moving through your brain, as your neurons pass tiny signals from one to another, letting you follow these words. Every breath you take, every gentle rise and fall of your chest, is made possible by atoms and molecules that follow quantum rules. You spend your whole life floating on the surface of this deeper world without ever having to notice it. Tonight, we're simply pausing long enough to acknowledge that the surface isn't all there is. Physicists sometimes describe this realm as the scale where the wave nature of matter becomes important. That sounds abstract, but it just means this. When you go small enough, the universe stops behaving like a collection of solid, separate pieces and starts behaving more like a set of overlapping possibilities. Instead of asking, where is this particle exactly? You start asking, where is it likely to be? Instead of, what is it doing right now? You ask, what might it do if I look? Even some of the greatest scientific minds struggled with this. Albert Einstein famously objected to the idea that chance could sit at the heart of reality. God does not play dice with the universe, he wrote, pushing back against the idea that probabilities and possibilities could be fundamental. But decade after decade, experiment after experiment has quietly suggested that at the smallest scales, the universe really does seem to roll its own peculiar kind of dice. And somehow, out of that strange game, our solid, everyday world emerges. You don't need to wrestle with the equations behind all of this. It's enough for now just to let the idea rest in your mind. Beneath everything familiar lies a layer where objects can act like waves, where outcomes remain open until they are nudged into place, and where your act of looking plays a small but real part in how the story unfolds. In a moment, we're going to explore the main ways this hidden layer shows itself. 4 recurring patterns of behavior that quietly shape everything from starlight to the atoms in your hands. For now, you can simply let the thought settle. The world you move through each day is only the surface. Just beneath it, the quantum realm is always there, quietly humming with possibilities. To understand just how unusual this tiny world is, it helps to start with one of its simplest tricks. In everyday life, we're used to things behaving in a very straightforward way. A wave is a wave. A solid object is a solid object. The ocean spreads and ripples. A baseball flies along a clear, predictable path. We don't confuse the two. One belongs to the language of fluid motion, the other to the language of solid matter. At the quantum scale, those two languages blend into one. Here, every piece of matter and every particle of light can act like both a tiny grain and a flowing wave, depending on how we choose to look at it. This idea is called wave-particle duality, and it sits at the heart of quantum mechanics. It sounds abstract, but its meaning can be felt in a simple picture that physicists have returned to again and again: the double-slit experiment. Imagine a dark wall with 2 narrow openings side by side, 2 slits that particles or light can pass through. Behind that wall is a screen that records where things land, like a very sensitive photographic plate. If you were to fire tiny pellets, like BBs, at the wall, you'd expect them to either hit the solid parts and bounce off, or slip through one slit or the other and strike the screen behind. Over time, the screen would show 2 bright bands where most of the pellets pass through, 1 band behind each slit. That's the pattern of particles: neat, separate, localized. Now, imagine sending waves, like gentle ripples on the surface of a pond, toward those 2 openings. Each slit would act like a new source of ripples. The waves spreading out from the left slit and the waves spreading out from the right slit would meet and overlap. Where crest meets crest, they add together and become brighter. Where crest meets trough, they cancel and become dimmer. On the screen behind, you no longer see just 2 bright regions. You see a whole series of alternating light and dark stripes, an interference pattern. That's the signature of a wave, a pattern carved by overlapping possibilities. When physicists send light through the double slits, they see that wavy pattern. Light behaves as if it has passed through both openings at once, interfering with itself in midair. But the real shock comes when you turn down the intensity so low that you send 1 particle of light at a time, 1 photon, like a single tiny bullet of energy. You might expect the photons to behave like pellets now, hitting the screen in two simple bands. Instead, if you wait patiently and let those tiny specks build up, they slowly form the same interference pattern as a wave. Each individual photon arrives as a little dot, but together they draw a picture that says, "I acted like a wave on the way here." It gets stranger. If you place detectors at the slits to check which opening each photon went through, the interference pattern disappears. The picture on the screen shifts to the simple, particle-like pattern of two bands. By trying to find out which path the photon took, you've changed how it behaves. Careful modern versions of this experiment, refined at places like MIT, keep confirming the same odd truth. Light is neither just a wave nor just a particle. It can show either face depending on how we ask the question. Think of it like a friend who seems to live a double life. At work, you see them in one mode, precise, focused, polished. At home, they're relaxed, playful, spontaneous. If you only ever saw them at the office, you'd swear they were one kind of person. If you only ever saw them on a lazy Sunday afternoon, you'd swear they were another. The reality is that both sides are completely real, and which one you meet depends entirely on the situation. Quantum objects are like that. Under some conditions, they show their particle side, landing in clear, sharp spots on a screen. Under other conditions, they reveal their wave side, spreading out into patterns of probability and interference. You never quite see both at the same time, but you can't deny either aspect. Physicists at places like Stevens Institute of Technology have even developed mathematical descriptions that assign a kind of wave score and particle score to these quantum systems, quantifying how much of each behavior is present. This isn't just a curiosity tucked away in theory. Learning how to control and tune this dual nature opens doors to new technologies. Sharper quantum imaging that can see details beyond classical limits. Ultra-sensitive quantum sensors that can pick up tiny changes in fields and forces. And communication systems that encode information in both wave-like and particle-like aspects of light. As if that weren't enough, there's an even more whimsical twist hiding in this first pillar of quantum strangeness. Something physicists have nicknamed the quantum Cheshire cat, after the grinning cat in Alice in Wonderland that can fade away and leave only its smile hanging in the air. In certain carefully designed experiments, researchers have managed to separate a particle from one of its properties, at least in a subtle, statistical way. For example, they can send a single photon through a setup where its physical presence takes one route, while a property like its polarization, the orientation of its internal vibration, effectively takes another. When they look at the results, it's as if the particle went one way, and its grin went another. To bring that down to something more familiar, imagine standing in front of a mirror. Usually your reflection stays perfectly tied to you. If you walk to the left, it walks to the left. If you raise your hand, it does the same. Now, picture a world where you could somehow step out of the room, but your reflection remained, still waving back, still smiling, even though your body had moved elsewhere. That's not something you will ever see in your bathroom mirror. But at the quantum scale, nature plays games that feel just that strange. The particle and its property, once thought to be inseparable, can be teased apart in ways that challenge our deepest assumptions about what an object even is. So, this first pillar, wave-particle duality, is already more than enough to stretch the imagination. It tells us that the pieces of reality are not locked into a single rigid identity. They can be discrete and localized, or spread and wave-like. Their properties can behave as if they have a life of their own. And somehow, out of all this flexibility, the familiar world of chairs and phones and coffee mugs still manages to appear solid and dependable. As you lie there listening, you don't need to hold all the details tightly. It's enough to let a simple impression sink in. At the smallest scales, the universe refuses to be just one thing. It carries multiple faces and reveals the one you ask to see. And if a single photon can be both a particle and a wave, if a property can wander away from the thing it belongs to, then a gentle question begins to arise. What happens when reality doesn't just wear two faces, but holds many different possibilities at once, waiting to see which one will be called into being? There is another layer to this strangeness that goes beyond having two faces. It's not just that a quantum object can behave like a wave or a particle. It's that, for a while, it doesn't have to choose any single outcome at all. In the world you move through every day, things seem to be very definite. A light switch is either on or off. A door is either open or closed. When you think about information in a computer, it's the same idea. Each bit is a tiny switch, a 1 or a 0, yes or no. Our entire digital world is built on that kind of clarity. Quantum mechanics quietly replaces that clarity with something softer. At the smallest scales, the basic units of information are not bits, but qubits, quantum bits. And a qubit doesn't have to be locked into just 0 or just 1. It can rest in a blend of both possibilities at the same time, described by smooth, wave-like probabilities. Only when you ask the qubit a question, only when you measure it, are you forced to get a single answer. This in-between condition is called superposition. It's as if reality is willing to hold multiple stories at once, keeping all of them alive in a quiet, overlapping way until something comes along that demands a decision. To feel this more intuitively, imagine a calm, empty room with a single lamp in the center and two light switches on opposite walls. In the ordinary world, one switch might turn the lamp on, the other might turn it off. At any given moment, the lamp is either glowing or dark. There's a clear state. Here, in the quantum picture though, before anyone checks, the situation isn't so rigid. It's as if the lamp is in a gentle blend of on and off, both possibilities encoded in the underlying wave of probability. Only when someone finally opens the door and looks, does the room commit to being bright or dim. Until that moment, the state of the lamp is more like a soft cloud of options than a single fixed fact. That might sound like pure abstraction, but nature has been quietly taking advantage of this for billions of years. When sunlight hits a leaf, the energy from each photon has to travel through a maze of molecules to reach the reaction centers that drive photosynthesis. You might picture that energy choosing a particular path and marching along it like a tiny courier on a single road. If that were all that happened, the process would be much less efficient than it is. What seems to happen instead is more elegant. The energy doesn't commit to one route right away. It spreads out in a quantum way, exploring many paths at once in a delicate superposition. Through this, it can sample different possibilities and naturally favor the pathways that lead most efficiently to the reaction centers. The result is near-perfect energy transfer, far better than a simple classical hop from point A to point B. In other words, Leibs have been using quantum superposition as a search strategy long before humans even had the language to describe it. Scientists see hints of this same principle in other places too, in the way certain molecules transport energy, in the subtle inner workings of biological systems, even in the way some materials conduct electricity. Nature seems very comfortable letting things exist in blended, overlapping states when it helps get the job done. And it's not confined to particles or tiny clusters of atoms. Researchers have built delicate devices, a kind of piezoelectric tuning fork, for example, made of around 10 trillion atoms. Under carefully controlled conditions, they can nudge this object into a quantum state where it is both vibrating and not vibrating at the same time. 10 trillion atoms, resting in a superposition of motion and stillness. You can picture it like a tiny bell that has, in some sense, rung and not rung together. Its future sound suspended in a cloud of possibility until the right kind of observation is made. Experiments like this blur the line between the quantum world and the everyday one. For a long time, it was easy to believe that quantum weirdness belonged only to electrons and photons, while larger things were forever locked into definite states. But as our tools grow more precise, we keep finding that the boundary is not as sharp as we thought. larger and larger systems can be coaxed into these ghost-like combinations of possibilities, at least for a brief, fragile moment. To capture the emotional weight of this, physicists often turn to a thought experiment you may have heard of, Schrödinger's cat. In the story, a cat is placed in a sealed box with a device that has a quantum trigger, perhaps the decay of a single atom. If the atom decays, the device releases a poison and the cat dies. If the atom doesn't decay, the cat lives. According to the rules of quantum mechanics, before the box is opened, the atom is in a superposition of decayed and not decayed. It hasn't chosen yet. Push that idea all the way, and you're forced into a strange conclusion. Before the box is opened, the cat is, in some sense, both alive and dead at the same time. No one is suggesting we will ever put an actual cat into such a situation, but the story gives you a feel for how radical superposition really is. It asks you to imagine that, at a certain level, reality is capable of holding incompatible outcomes together, not as a metaphor, but as a genuine physical state. Of course, in practice, we never see cats in such mixed conditions. By the time you lift the lid, one outcome has already won. The cat is either clearly alive or clearly gone. Somewhere between the quantum trigger and your conscious observation, the fragile superposition collapses into a single storyline. Part of the ongoing mystery of quantum mechanics is understanding exactly how and when that collapse happens, and what counts as a measurement. For our purposes tonight, you don't have to wrestle with the technical details. You can simply rest with the idea that at the deepest levels, the universe is extraordinarily patient with possibility. Particles, clusters of atoms, and even small mechanical objects can rest in soft, overlapping states, with many potential futures coexisting quietly in the background. You can think of it as reality holding its breath, keeping multiple options open until something, an interaction, a measurement, a touch from the environment, nudges it toward a single outcome. Possibilities don't simply vanish. They're gently folded together into a superposed state, waiting for attention. As you lie there, you might notice how this echoes in your own experience. Before you make a choice, your day contains many potential paths. Go here, stay there, call someone, say nothing. For a moment, all of those futures are alive in your mind, layered on top of each other, before you finally move in one direction. Quantum superposition operates on a much more literal and precise level, but the feeling of suspended possibility is something you already know. Wave-particle duality showed us that quantum objects refuse to fit into a single simple category. Superposition shows us that they can refuse to pick a single definite state, living instead in a blend of outcomes that only resolves when the universe is forced to decide. And once you accept that a single particle, or even a tiny mechanical object, can inhabit multiple possibilities at once, another question naturally begins to surface. What happens when these possibilities don't just belong to one thing, but link different things together, so that a choice made here is mysteriously tied to what happens over there? If superposition is the story of one thing holding many possibilities, entanglement is what happens when those possibilities become shared. Picture two tiny particles born together in the same quantum event, like twins emerging from the same brief flash of energy. From that moment on, they are linked in a way that doesn't fit our everyday ideas of separation. You can send one far away across a lab, across a city, even into space, and yet, in a very real sense, they remain parts of a single connected system. In classical thinking, if you measure one of them, you simply learn something about it. In the quantum world, when you measure one, you also determine the state of its partner instantly, no matter how far apart they are. Change the kind of question you ask here, and the answer over there adjusts to match as if there were an invisible thread tying their fates together. Albert Einstein struggled with this deeply. He called it spooky action at a distance because it seemed to violate the comforting rule that influences must travel through space step by step, never faster than light. For a long time, many people hoped that some hidden mechanism would rescue our common sense. That entanglement was just a temporary misunderstanding. But as the decades passed, experiments kept getting sharper, more precise, more ambitious. Physicists sent entangled photons, tiny particles of light, through long optical fibers, then between mountaintops, and eventually between ground stations and orbiting satellites. They kept asking the same question: are these particles really correlating their answers in a way that no classical explanation can reproduce? Over and over, the universe gave the same reply: yes. Today we've seen entanglement hold across distances of hundreds of kilometers, and even over 1,000, with particles behaving as if space between them simply doesn't matter for certain shared properties. Nothing material is flying back and forth faster than light, but the information encoded in their relationship defies the limits we once thought were absolute. And this isn't just happening out there in the cold night sky, it's happening inside you. Within every proton in your body, deep in the nucleus of each atom, there are smaller constituents, quarks, and the gluons that bind them together. Calculations and experiments suggest that these components are not just loosely associated. They are maximally entangled, locked into a web of correlations that help give the proton its stability and structure. The solidity you feel when your hand rests on a pillow or the mattress beneath you depends in part on these invisible bonds. So, even as you lie still, there is a constant intricate conversation going on at scales far too small to see. Within every atom of your body, connections are being maintained that stretch across distances 1 trillion times smaller than the width of a human hair. You are quite literally built from entanglement. Human beings are also learning how to use this phenomenon in our technology. One of the most promising ideas is quantum communication, where entangled photons carry information in a way that is fundamentally different from conventional signals. When two parties share entangled particles, they can use the correlations between measurement outcomes to build secret encryption keys. The remarkable thing is that any attempt to eavesdrop inevitably disturbs the entangled state. In other words, if someone tries to listen and the delicate quantum link is broken and both ends can see that something has gone wrong, security is no longer just a clever math problem. It's protected by the basic laws of physics. This is the dream behind unbreakable quantum encryption communication systems, where privacy comes from nature itself. Beyond communication, entanglement sits at the heart of quantum computing and quantum sensing, allowing many particles to act as a coordinated whole rather than as isolated bits. When qubits are entangled, the information they carry spreads across the entire collection, enabling patterns of computation that would be impossible for classical machines. In quantum sensors, entangled states can make measurements more precise, letting us detect faint signals, tiny shifts in fields, forces or time that would otherwise be lost in noise. But beneath all these applications, there is a deeper, quieter message. Entanglement tells us that the universe is not simply a collection of separate things, each minding its own business. At a fundamental level, it behaves more like a single woven fabric, where threads that start together can remain connected even when they are pulled far apart. Some of the properties of the world cannot be assigned to individual objects at all. They belong instead to the relationships between them. It's easy to feel alone in your own mind, especially late at night. Yet, on the level of quantum physics, isolation is not the default. Connection is. The particles that make up your body have spent their entire existence in states of relationship with each other, with fields around them, with the wider universe. The notion of being completely separate is in some ways the illusion. Of course, there are limits to what entanglement can do for us. It doesn't let us send messages faster than light or magically control distant objects. The correlations it creates are powerful, but they come with strict rules, as if the universe is gently reminding us that some boundaries still stand even in this realm of mystery. And that brings us to another quieter feature of the quantum world. Even when particles are intimately connected, there are things we are simply not allowed to know with perfect precision at the same time. Certain pairs of questions about where something is and how fast it's moving, for example, refuse to yield exact answers together, no matter how careful we are. So, after drifting through this web of connections that reach across space, we're about to step into a different kind of limitation. Not about distance, but about knowledge itself, and the soft, unavoidable fuzziness built into the foundations of reality. Up to now, we've been wandering through a world where particles can share identities and stretch their connections across space. But there is another quieter rule that shapes everything. At the smallest scales, a rule about how much the universe will actually let you know at once. In classical physics, it feels natural to imagine that if you just had a perfect enough instrument, you could measure anything as precisely as you want. You could pin down exactly where something is and exactly how fast it's moving at the same time, with no limits except our technology. Quantum mechanics gently says no. Heisenberg's uncertainty principle tells us that some pairs of properties simply refuse to be nailed down together. The more sharply you know a particle's position, the fuzzier its momentum becomes. The more precisely you know how fast it's moving, and in which direction, the less clearly you can say where it actually is. This isn't a failure of microscopes or a bit of experimental noise we haven't cleaned up yet. It's built into the structure of reality. At the quantum level, there is a fundamental blur, a softness around the edges of what things are doing. You might picture trying to photograph a dancer in a dimly lit room. If you use a very short exposure, you can freeze the position of their body in mid-movement, but the sense of motion is lost. If you use a longer exposure, you see sweeping trails of movement, but no sharply defined pose. You can capture a perfect still frame or a perfect sense of motion, but not both at the same time. The act of choosing one kind of picture sacrifices the other. Something like that is happening in the quantum realm, but much deeper. The very questions we ask about particles shape what can be answered. Reality does not hand us a complete sharp photograph of everything at once. Instead, it offers a delicate balance between what can be known here and what must remain uncertain there. And strangely, this limitation is not a problem to be solved. It's the reason anything stable exists at all. If position and momentum could both be pinned down with infinite precision, atoms would be in trouble. Electrons would be forced into tiny, tightly confined orbits around atomic nuclei. With no room for uncertainty, the energy of those electrons would spike, and the structures of atoms as we know them would collapse. Chemistry would unravel. Stars could not shine in their gentle, steady way. The familiar world would not form. The uncertainty principle gives particles room to spread out to occupy fuzzy regions rather than sharp points. That fuzziness stabilizes atoms. It lets electrons occupy hazy clouds instead of rigid tracks, and those clouds allow rich patterns of bonding and interaction. Out of that softness, you get molecules, cells, oceans, planets, and the complex web of life. The universe at its core needs a little imprecision so that structure and variety can exist. If you like, you can think of it as a kind of cosmic breathing space. Instead of a world where everything is locked into exact positions and exact motions never able to shift, we live in a reality where there is always a bit of give. A little uncertainty that leaves room for change, creativity, and surprise. Now, bring this together with the other quantum features we've met. Wave-particle duality shows that light and matter can move like waves, yet arrive like particles. Superposition allows systems to hold many possibilities in suspension at once. Entanglement ties distant parts of the universe into single shared states. And uncertainty sets gentle limits on what can be known, keeping the whole structure from freezing into something rigid and lifeless. Taken together, these aren't just separate oddities. They form a kind of hidden music, four interwoven themes playing underneath everything you see and feel. The waves, the overlapping possibilities, the invisible connections, and the soft blur of what can be known all blend into what some physicists like to call a quantum symphony. You don't hear this symphony with your ears, but you live inside its consequences. The warmth of starlight, the solidity of your pillow, the chemistry of the cells in your body, all of them depend on this underlying arrangement of rules and limitations. Even the thoughts drifting through your mind right now are carried by particles that obey these quiet constraints. As you rest with that idea, you might imagine the universe as a vast dark concert hall filled with an orchestra no one can see playing a piece that never ends. For most of human history, we only heard the loud classical notes, the familiar motions of planets and falling apples. Only recently have we begun to notice the softer quantum instruments underneath, setting the rhythm. And in laboratories around the world, scientists are learning not just to listen, but to tune small pieces of matter, so they resonate with this deeper score, creating strange new phases of quantum stuff that behave less like ordinary solids and more like liquid light or information-rich vapor. Up to this point, the quantum world has mostly been a kind of invisible score underneath everything familiar, a symphony of waves, possibilities, connections, and uncertainty. But in a few quiet laboratories, people are doing something even stranger. They're learning how to play that music on command by building new kinds of matter that don't quite fit our old categories of solid, liquid, or gas. Imagine holding a small, dark crystal between your fingers. To your eyes, it might look utterly ordinary, just another chunk of material. But inside, electrons and their missing partners are moving in a way that starts to look less like individual particles and more like a single shared quantum fluid. In one line of research, a team at UC Irvine has been studying a compound with the heavy name hafnium pentatelluride. Deep inside this material, electrons and holes, tiny absences of electrons that behave like positively charged particles, can pair up and form what physicists call excitons. You can think of an exciton as a brief flickering relationship between an electron and a whole, a little bound state of energy, rather than a solid object. Under the right conditions, an entire crowd of these excitons can start to move together, not like individual marbles rolling around, but like a coordinated liquid made of quantum relationships. The material begins to act as if it contains a strange new phase. Not quite a normal, solid, not quite a typical liquid, but a kind of quantum liquid where the important thing is the pattern of connections, rather than the motion of individual particles. From a distance that might sound abstract, but it points towards something almost magical. Materials that could carry energy in especially efficient, robust ways. Some of these excitonic phases seem as if they could, in principle, store and move charge without losing much to heat and tolerate conditions that would normally damage ordinary electronics. That's why scientists talk about them as candidates for deep space technology devices that might endure cold radiation and long years of use far from the shelter of Earth. Alongside these quantum liquids, there are quantum liquid crystals. In a familiar liquid crystal display, molecules line up in neat patterns that can be nudged and twisted by electric fields, which is how your screen forms letters and images. A quantum liquid crystal is similar in spirit, but the thing that lines up isn't just the positions of atoms. It's the way electrons themselves flow and organize. In some of these materials, the electrical conductivity suddenly drops in certain directions, while remaining higher in others. The electrons seem to agree on preferred paths, as if they're choosing lanes on a cosmic highway. At the same time, the material can be unusually resistant to radiation and disturbances because the electrons are locked into a shared quantum pattern that is harder to disrupt one particle at a time. It's the kind of behavior engineers dream about matter that naturally protects itself, channels energy cleanly, and remains stable even in harsh environments. You could imagine future spacecraft or satellites quietly relying on such phases, crystals that double as shields, wires, and memory all at once. And yet even this is only part of the story. It isn't just matter that can change phase, information can too. To get a feeling for this, think again about water. At low temperatures, molecules freeze into ice, rigid, ordered, with each piece locked into place. Warmed up, the ice melts into liquid water. Molecules flow, bump, and slide around one another. Heat it further, and you get steam. The molecules separate and fly freely. Physicists studying quantum systems have started to see similar patterns in the way information itself behaves inside many particle states. In some regimes, quantum information is locked into rigid patterns, highly ordered with entanglement shared in very specific ways. In others, that information becomes more fluid, rapidly spreading through the system, scrambling and mixing as particles interact. With more energy and interaction, it can become almost vapor-like, diffused throughout the whole system in a way that's hard to untangle. What controls these shifts isn't temperature alone, but the balance between entanglement and measurement, between how strongly parts of the system share quantum correlations and how often those correlations are disturbed or observed. Adjust that balance and the phase of the information changes. Researchers talk about phase transitions of quantum information because mathematically, these shifts can resemble ice melting or water boiling. Only the thing that is freezing or flowing is not just matter, but the structure of correlations and knowledge in the system. Why does this matter for you, lying there in the quiet of your room? Because the devices that might one day sit on a bedside table or orbit high above the Earth will be built from exactly these kinds of insights. Quantum computers rely on carefully crafted phases of matter, where qubits, those superposed bits of reality, can hold their delicate states long enough to perform calculations. Quantum memories and sensors depend on patterns of entanglement that are robust like ice, yet flexible enough to respond to subtle signals like liquid. The strange crystals and liquids being probed in these experiments are early hints of a future where materials are designed not just for strength or weight, but for the way they host and protect quantum information. They are prototypes for a world in which the magic tricks of the quantum realm, superposition, entanglement, and that subtle interplay of knowing and not knowing are woven right into the technology around us. You might picture shelves of these materials as a kind of palette in a painter's studio. Each new phase of quantum matter offers its own texture. Some carry currents with almost no resistance. Some shield against radiation. Some support long-lived entanglement or rapid information flow. By choosing and combining them, engineers will be able to compose devices that listen more carefully, compute more deeply, or survive far longer in the dark between the stars. All of this, for now, happens at scales too small to see thin films on chips, tiny crystals cooled in carefully controlled chambers. But the direction is clear. We are learning how to persuade large collections of atoms to act as one quantum system, to hum along on the same hidden melody. And once you start to gather atoms into those shared states, it's natural to wonder how large you can go. Not just electrons in a crystal or excitons in a strange new liquid, but objects big enough to almost glimpse with the naked eye. Tiny beams, vibrating membranes, drums etched into metal. What would it mean for those to move, according to quantum rules, carrying that invisible symphony up toward human scales? Now that we've met these strange new phases of quantum matter, let's gently zoom out, not all the way to everyday life, yet just a little closer to it. For a long time, quantum mechanics was something that seemed to belong only to the tiniest scales, electrons and atoms, photons, in a beam of light particles darting around in accelerators. But in a few very careful experiments, researchers have started to coax larger objects into playing by quantum rules. Not just individual particles, but pieces of machinery you could almost see with the naked eye. Imagine for a moment two tiny silicon beams, each about as thin as a human hair and a fraction of the length. They're anchored at their ends like the tines of a microscopic tuning fork, able to vibrate up and down when gently excited. On their own, they would be simple mechanical objects governed by the familiar rules of springs and masses. But in a quiet laboratory under carefully controlled conditions, those beams can be cooled and tuned until their vibrations stop behaving like two separate instruments. Through the careful use of light or microwaves in a cavity, their motion can become entangled. When one beam quivers, the other responds not through any obvious push or pull, but through a shared quantum state that links them. You can picture it like two orchestras placed on opposite sides of a valley. If each played independently, you'd hear a messy overlap of sound. But in these experiments, it's as if the musicians on both sides are following the same invisible conductor. A note struck on one side is mirrored in the timing and tone on the other, even though the players never exchange a glance. The two silicon beams become parts of a single delicate quantum performance. In another set of experiments, scientists have taken this idea even further, with small aluminum drum heads etched onto a chip of silicon. Each drum is many billions of atoms across a genuine mechanical object, not just a handful of particles. When cooled close to absolute zero and coupled to the right electromagnetic fields, these drums can enter an entangled state as well. You might imagine two tiny circular membranes, like microscopic speaker cones mounted side by side. Left alone, each would simply vibrate according to whatever energy is fed into it. But when they're prepared in a quantum state, their vibrations become linked. If one drum moves inward, the other moves outward in a coordinated way that cannot be explained by a simple mechanical connection. Trillions of atoms on one drum share a quantum story with trillions on the other. For a long time, it was easy to think of the quantum world and the everyday world as living in separate boxes, one for the strange behavior of particles, one for the reassuring rules of notebooks, coffee cups, and musical instruments. These experiments blur that boundary. They show that with enough care, an object made of countless atoms can still be coaxed into a single fragile quantum state, where its behavior is described not by individual pieces, but by a shared wave of possibility. This isn't just a curiosity. When you can make macroscopic objects follow quantum rules, you gain access to new kinds of sensors and measuring devices. An entangled pair of mechanical resonators can respond to tiny disturbances, a passing vibration, a faint tug of gravity, a subtle change in the surrounding environment in ways that classical devices cannot easily match. Engineers imagine using such systems as exquisitely sensitive ears, capable of hearing the softest whispers in the fabric of space-time, minute gravitational waves, shifts in local fields, or even the faint signatures of geological or biological processes. A drum or beam in a quantum state can in principle be used to detect changes that would otherwise be lost in noise, because its whole pattern of motion is protected and correlated by entanglement. You can think of it as giving matter a new way to listen. Instead of each atom jostling on its own, the entire object listens as a unified whole. A disturbance at one point is reflected in the shared quantum state, making it easier to pick out a signal from the random background. The object becomes less like a collection of parts and more like a single coherent antenna tuned to the universe. Of course, these devices are still fragile, and they live in refrigerators much colder than the depths of interstellar space. They're not sitting on desktops or in bedside gadgets just yet, but they show something important. Quantum behavior doesn't stop at the edge of the microscopic world. With enough control, you can invite larger and larger systems into the quantum dance. And once you realize that, a deeper question starts to form in the background of the mind. If entire drums and beams can be drawn into a shared quantum state, if we can make pieces of metal and silicon behave like giant wave functions, what else might be possible? What other parts of reality could be persuaded to reveal their hidden quantum side? In particular, you might begin to wonder about something that sounds almost like a contradiction in terms the emptiness between things. The space between atoms, between planets, between galaxies. If we can coax solid objects into quantum motion, what might we eventually learn to draw from the so-called vacuum itself, from the restless sea that lies beneath what we usually call nothing? When most of us picture nothing, we imagine an empty room, a blank page, a quiet stretch of sky between the stars, stillness, absence, a kind of cosmic zero. But in quantum physics, nothing is one of the busiest places there is. If you could somehow shrink down and peer into what we casually call empty space, the space between your hands, between distant galaxies, even between the particles in your own body, you wouldn't find a smooth, silent void. You'd find a restless sea of activity. fields trembling ever so slightly, tiny flashes of energy appearing and fading before they can fully become anything at all. Physicists call these vacuum fluctuations, and the quantum view fields are never perfectly flat. Even when you remove all matter, all light, all heat, what's left behind still hums with uncertainty. That uncertainty shows up as brief ghost-like excitations, virtual particles that pop into existence as pairs and then recombine and vanish. They're not particles in the everyday sense, but they leave fingerprints, tiny shifts in energy levels, delicate forces between objects, subtle corrections that have to be included for our theories to match what experiments see. So, the vacuum is less like a clean countertop, and more like a pot of water that looks calm on the surface while down below, small currents and eddies constantly form and dissolve. On human scales, it feels like nothing. On quantum scales, it's always in motion. Recently, theorists and experimentalists have begun to ask a very bold question. If the vacuum is full of this jittery activity, can we do anything with it? Can we in some controlled way reach into this sea of fluctuations and guide how energy moves within it? In a few carefully designed thought experiments and early lab setups, researchers have shown that, at least in principle, you can. By arranging the right kind of quantum fields and by making precise measurements on one region of space, it's possible to influence how energy behaves in another region without sending any physical object across the gap. It's sometimes described as teleporting energy, though it doesn't violate relativity or allow faster-than-light signals. Instead, it's more like learning how to surf on waves that were already there. Imagine two small, quiet patches of space side by side. To the naked eye, they look identical, just emptiness. But if you treat the vacuum as a quantum field and you interact very gently with one region, measuring it in a carefully chosen way, you can change the pattern of fluctuations there. That change in turn alters the correlations it shares with the neighboring region. With the right setup, energy can be drawn out of that second region in a way that wouldn't have been possible before. No particles fly from A to B. Instead, you've used information and measurement to reshape the vacuum's own background ripples, and then you've extracted usable energy from a place you never touched directly. It's an effect that only makes sense when you fully accept that empty space isn't truly empty. All of this is still at the level of highly controlled conditions and very small scales. You won't see vacuum power plants on the corner anytime soon, but it sketches the outline of where quantum technology is slowly heading. We're not just observing quantum fields anymore, we're starting to gently engineer them. The same deeper understanding that lets you coax energy along invisible pathways also underlies the technologies quietly taking shape in labs around the world. Quantum communication networks that use entangled photons to send information with security guaranteed by the laws of physics. Quantum sensors that rely on delicate superpositions to detect faint magnetic fields, tiny changes in gravity, or the slightest motion. Quantum-enhanced measurement techniques that turn noise itself into a kind of resource rather than a limitation. Right now, much of this is still housed in polished metal cryostats and racks of electronics, tended by patient graduate students working late into the night. But piece by piece, it's moving outward. The strange behavior you've been hearing about the coin that's both heads and tails, the particles that share a state, across distance the vacuum that can lend energy if you ask, in just the right way, is being turned into circuits, protocols, and devices. It's easy to hear words like quantum revolution and think of movie trailers or breathless headlines. In truth, it's usually quieter than that. It arrives as slightly better timing in a satellite link, as more accurate navigation, as medical imaging that can see a little deeper, as measurements that let us understand our climate, our materials, and our own bodies with more subtlety. But underneath those practical improvements lies something more profound, a growing ability to shape and harness the patterns written into the fabric of reality itself. Not just matter, not just light, the fields and fluctuations that fill the spaces in between. And as you rest here floating with these ideas, another thought begins to surface almost on its own. If the vacuum is alive with invisible motion, If matter and energy can be guided and entangled and coaxed into new forms, where do you fit into that picture? What does it mean for a conscious mind to arise in a universe like this and to watch these quantum patterns unfold? All of these strange effects we've been talking about, superpositions, entanglement, energy drawn from emptiness, quietly circle around one very simple question. What makes one outcome real and all the others fade away? In the equations of quantum mechanics, a particle doesn't have to choose a single path. It can explore many possibilities at once, like a soft cloud of maybes. A photon can go through both slits. An electron can be in several locations. A whole system can exist in a blend of states we call a superposition. Yet, when we finally look, the world presents a clear answer. The detector fires here, the atom decays. Now the pointer on the dial settles on one definite value. That jump from a spread-out haze of possibilities to one concrete result is known as the measurement problem. The math tells us how the cloud evolves over time, and it tells us the probabilities of each outcome. What it doesn't tell us, at least not in a straightforward way, is what exactly counts as a measurement, or why this act should have such a special role. You might picture a scientist in a lab pressing a button on a machine. Is that the moment reality chooses? Or does it happen earlier inside the detector electronics? Or later when the data appears on a screen? Or only when a conscious mind finally becomes aware of the reading? Some interpretations of quantum mechanics say, we don't need to invoke consciousness at all. They point to a process called decoherence as a quantum system interacts with its environment, air molecules, stray photons, vibrations. It rapidly loses its fragile superposition, becoming entangled with so many degrees of freedom that interference patterns wash out. To us, it looks like the system has collapsed into one outcome, even though, in a deeper sense, the full quantum state is still spread out over many possibilities. Decoherence explains why we don't see everyday objects in obvious superpositions. Your coffee mug doesn't appear both on the table and on the floor because it's constantly bumping into countless particles and fields that effectively measure it all the time. The world feels classical because it's bathed in an environment that shreds quantum coherence almost instantly. But there's a lingering puzzle. Decoherence describes how superpositions become hard to see. It doesn't quite tell us why you, the observer, experience a single definite outcome, rather than some more diffuse multi-branch awareness. That gap is where questions about mind and measurement quietly slip in. For a long time, many physicists assumed that quantum coherence was too delicate to survive in anything as warm, wet, and noisy as a living system. Recently, though, experiments have shown quantum effects persisting longer than expected, even at room temperature inside certain materials, and intriguingly in some biological processes like photosynthesis. Nature, it seems, is better at sheltering quantum behavior than we gave it credit for. That has encouraged a small but persistent group of researchers to wonder whether the brain might, in some subtle way, be making use of quantum processes. Not in the sense of you consciously solving equations in your sleep, but in the possibility that the building blocks of your neural machinery could sustain tiny pockets of coherence that influence how information flows. At the same time, there have been experiments with devices called random event generators, machines, that produce sequences of bits based on quantum processes like radioactive decay or electron tunneling. In a few studies, when groups of people focus their attention or intention in a coordinated way, the statistics of those random streams appeared to tilt ever so slightly away from pure chance. The results are controversial and far from universally accepted, but they whisper an intriguing question. Could consciousness in some circumstances leave a faint fingerprint on quantum noise? It's important to hold all of this gently. Nothing here proves that mind collapses the wave function, or that human intention can reliably steer subatomic events. The evidence is mixed, often fragile, and easy to overinterpret. But even the fact that serious scientists are willing to test these ideas tells you something about how mysterious the measurement problem remains. What we can say without overreaching is that the border between the quantum world and the world of experience is not as clean as we once imagined. Coherence can survive longer than we expected. Entanglement can stretch across distances and systems we once thought were too messy. And the act of observing, even if we don't yet fully understand how, seems woven into the story of how possibilities harden into the single path you remember as your life. From here, a natural curiosity arises. If consciousness does have any quantum roots at all, what might that look like inside the brain? How could flickers of coherence and entanglement give rise to the seamless feeling of being a single aware self moving through the world? If the act of measurement really does sit at the heart of quantum reality, it's hard not to wonder what that means for you, for the strange, steady light of awareness that's listening right now. One bold proposal tries to bring these pieces together under a single roof. It's called OR, short for Orchestrated Objective Reduction, developed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. In their view, consciousness isn't just something that happens when enough neurons chatter together. Instead, they argue that deep inside those neurons, in tiny scaffolding structures called microtubules, quantum states form, evolve, and then collapse in a coordinated way. You can picture these microtubules as delicate tubular lattices running through your brain cells, like microscopic organ pipes or crystal frameworks. According to OR, the quantum states inside them don't collapse randomly. They build up and tangle, and then undergo a kind of collective click, a moment of objective reduction. Each of those orchestrated collapses, they suggest, corresponds to a single unified moment of conscious experience. Whether or not this theory turns out to be right, it speaks to a deeper puzzle, sometimes called the binding problem. Your brain is flooded with separate streams of information, color here, sound there, touch, memory, emotion. Yet you don't experience them as scattered pieces. You experience them as one scene, one thought, one continuous you. Some researchers have wondered if quantum entanglement could help with that binding. If different parts of the brain, different microtubules, different networks of neurons share entangled states, then information spread across space might still behave as a single coordinated whole. It would be like thousands of instruments playing in different rooms, yet all locked to the same invisible beat. On a larger scale, scientists have observed that the brainwaves of two people can sometimes synchronize when they interact deeply. Partners in conversation, a parent and child, a musician, and an audience. Most of that can be explained with classical mechanisms, shared sensory input, subtle cues, mutual feedback. Still, the image is suggestive, two nervous systems momentarily falling into step, as if their internal rhythms had reached out and brushed against one another. From there, some thinkers take an even wider step and ask, what if consciousness is not a product, but a receiver? In that picture, the brain is less like a generator and more like a tuning device. They imagine a broader field of awareness, something like a universal background of potential experience. Your brain, with its intricately organized structure and delicate timing, would then act like a radio tuning in to a particular station on that vast band. Your thoughts, your feelings, your sense of self would be one localized expression of a much larger, more subtle cosmic awareness. None of this is established fact. It's a way of trying to connect the stubborn mystery of subjective experience with the equally stubborn mystery of quantum measurement. But it resonates with another idea from physics, the notion of a participatory universe. John Wheeler, a pioneering physicist, once suggested that observers don't simply look at the universe, they help bring certain aspects of it into being. In quantum experiments, the choice of what to measure seems to shape what kind of past the system had. In delayed choice experiments, researchers can decide at the last moment how to measure a particle, and the results behave as if that late decision reaches backward, influencing whether the particle acted like a wave or like a localized point along its path. It doesn't mean you can rewrite history in any simple everyday sense, but it hints that the line between past and present, between possibility and fact, is more malleable than our common sense picture suggests. Observation appears not just to reveal a pre-existing reality, but to select one thread out of a web of potential histories, one storyline that solidifies into the version you remember. When you put these ideas side by side, the possibility of quantum processes in the brain, the hint of synchronization between minds, the image of a field of consciousness, and the participatory nature of measurement, you arrive at a gentle, intriguing thought. Your awareness might not be a passive spectator. It could be woven into the way reality chooses its path. Even if the details remain uncertain, there's something quietly comforting in that. Every moment of attention, every act of noticing becomes a small act of collaboration with the universe. You are not just watching the play. On some deep level, you may be part of the casting, the staging the way the script unfolds. And as soon as you start thinking of things this way, the language of physics subtly shifts. The world stops looking like a pile of separate objects and begins to resemble something more, like a living network of relations, a vast humming lattice of information, exchanging, updating, and remembering. Once you begin to see reality as woven from relationships and possibilities, another quiet idea slips into view. Maybe what truly matters at the deepest level is information itself. In everyday technology, information is built from bits. A bit is simple and stubborn. It's either a 0 or a 1, like a tiny switch that's firmly off or firmly on. All of your emails, videos, and photos are just unimaginably long strings of those little choices. In the quantum world, that tidy picture loosens. A quantum bit or qubit can be in the 0 state, the 1 state, or a superposition of both at once. It's more like a spinning coin than a coin lying flat heads tails and all the shimmering in between. When you knit many qubits together and let them entangle you, don't just get a slightly better version of a regular computer. The number of possible patterns grows explosively far faster than you can comfortably picture. A quantum computer takes advantage of that richness. Instead of checking one option at a time, it can let a whole cloud of possibilities evolve in parallel, allowing interference to amplify the right answers and cancel out the wrong ones. It isn't magic, but it feels close. Problems that would take classical machines longer than the age of the universe to fully explore become, at least in principle, reachable. That's why scientists dream of using quantum computers to model complex molecules and materials with exquisite precision, designing new medicines, new catalysts, new kinds of batteries and solar cells. They imagine quantum-assisted machine learning, where patterns in oceans of data might be recognized in ways that look almost like intuition. These are early days and much of it is still experimental, but the direction is clear. Information processed under quantum rules behaves differently, and that difference is powerful. As researchers push deeper, they have noticed that quantum information itself seems to undergo phase changes the way water does when it freezes to ice or evaporates into steam. By tuning how strongly qubits are entangled or how often they're disturbed by measurements, entire new phases of information appear, some robust and error-correcting, some fragile and chaotic. From this angle, matter and energy start to look like expressions of a more basic bookkeeping. A few physicists now speak as if information might be more fundamental than the stuff it describes, as though particles and fields are the visible traces of an invisible ledger of quantum bits. If that's true, then everything you are, your memories, your habits, the way your laugh sounds in a quiet room, could be seen as a particular pattern of quantum information, shaped and reshaped over a lifetime. In that sense, you become one way. The universe stores a story about itself. One local arrangement in which reality has learned to say, I am here and I am aware. It's a large thought, maybe too large to fully hold. You don't need to solve it or pin it down. You can simply let it rest beside you like a book closing softly at the end of the day, as we ease into the most restful part of our journey, and let all of these ideas blur gently towards sleep. Somewhere beneath the quiet rhythm of your breathing, the quantum world is still at work. Every atom in your body, every photon that brushed your eyes today, every electrical whisper that moved through your brain as you listened, all of it has been playing by those strange rules we've been exploring together. Wave and particle possibility and choice entanglement and uncertainty. All of that has been present in every heartbeat, every thought, every tiny moment of your day. You are not standing outside this story looking in. You are written into it. The same mathematics that describes electrons and distant galaxies also describes the chemistry of your cells. The same entanglement that links particles across vast distances also links your life to countless others, to the people you love, to the stars that forge the atoms in your bones, to the long unfolding history of the universe itself. You are one small luminous point in a web of relationships that stretches farther than you can imagine. And yet right now, none of that asks anything from you. You don't have to solve the mystery of consciousness or decide which interpretation of quantum mechanics is right. You don't have to hold the entire cosmos in your mind. It's enough to know that while you rest, the universe will keep doing what it does best, quietly weaving reality from countless tiny events layer upon layer, breath after breath. So, if your shoulders feel a little tight, you can let them loosen. If your jaw is clenched, you can let it soften. If your thoughts are still trying to organize the ideas we've talked about, you can give them permission to wander, to blur, to fade into something softer and more dreamlike. Imagine just for a moment that you were floating on a calm, dark ocean of possibility, supported, held, completely safe. Below you, the quantum realm continues its invisible dance, keeping atoms stable, stars shining, and your own body quietly alive. Above you, the wider universe stretches out like a deep star-filled sky, ancient and patient and endlessly vast. In that space, you don't have to do anything at all. You can simply be. If sleep is close, you can let it come. Let each exhale carry away a little of the day, every worry, every unfinished task, every sharp edge of thought, until what's left is just a warm, quiet awareness of being part of something immeasurably large and kind. Rest knowing that even with your eyes closed, you are still woven into the fabric of the cosmos. Rest knowing that you belong here completely, exactly as you are. And whenever you're ready, you can let yourself slip gently over that edge into sleep, while the deepest mysteries of existence keep watch around you, steady and serene.